focus on determining the type of reaction. Is it SN1? Is it SN2? And then actually looking at the mechanism. As we go through the mechanisms today, you are going to see that they're very similar to things that we've looked at before because we actually looked at reactions with halides at the very beginning of the alkene stuff. So this recap slide we've looked at already. We looked at this yesterday before we played the Kahoot. But just looking at these recap slides, this is the most important information on each type of reaction. So if you have a Post-it note or something that you want to put on this recap slide, so you can always flip back to it if you need. SN2 happens all at once. Now we'll talk more about the inversion of configuration, what that looks like. But because SN2 happens all at once, you have to have a strong nucleophile. So you have to have a strong nucleophile that comes in and attacks at the same time that the leaving group leaves. So since it's happening all at once, it's going to work best when there's less steric hindrance. If you have a tertiary carbon, you're actually going to have no reaction. You'll notice here that the tertiary carbons can't actually work because there's too much steric hindrance. And so when you have that strong nucleophile, it's going to attack, and your aprotic solvent works the best. So your aprotic solvent is something that cannot hydrogen bond, and that's because it allows that nucleophile to stay strong with that negative charge. And then SN1, so this, remember the 1 means that there is one reactant in the rate determining step, so it happens over multiple steps. Typically we see it in 2. I'll show you how sometimes it could be 3 depending on the solvent. But you have a carbocation that forms. So since you have a carbocation that forms, you have to pay attention to the stability of carbocations. So tertiary, secondary will always work, but it cannot work with primary or with alpha carbons. Any type of nucleophile can actually work because you already have a carbocation forming, but the protic solvent actually favors SN1 because it works to stabilize the carbocation. So we've looked at all of these things already, but I did put these on the slide. So protic solvents, remember, can hydrogen bond. Aprotic cannot. So if you're looking at the type of solvent that exists, you just want to ask yourself, can it hydrogen bond? Remember when we talked about acids and bases in AP Chem? Protic, right, a proton, we're talking about hydrogen. So protic solvent is looking for something with hydrogen bonding. Aprotic cannot. So what we'll do is we'll look at this first slide, so this first practice. I'm going to kind of talk you through step by step what you should be looking at. Kind of where we should look at first, then second, then third. So for this, we're determining the reaction type. So we're going to have to circle what type of reaction, or does one not occur at all. Then we'll look at the mechanism, and we'll look at the products. We are going to pay attention to stereochemistry as well. So when it says inversion of stereochemistry, we're not going to go through and redesignate R versus S. When we talk about inversion of stereochemistry, if this is a wedge, our product would be a dash. So when we look at this is kind of the order that we need to go through as we're looking at SN1 versus SN2 and what type of reaction would occur. So first is the type of carbon. When you look at that alpha carbon, so this carbon that I just put a dot on, this is the alpha carbon. It's the carbon that we're focusing on. Right? The carbons one out are your beta carbons. So for this alpha carbon, we want to look at its degree, right? Its substitution. Is it primary, is it secondary, is it tertiary? That's just how many other carbons is it connected to. So what would be the degree of this alpha carbon? How many other carbons is it connected to? 2, right? So this is a secondary. Now a secondary carbon can undergo either SN1 or SN2. So we're not limited by the type of carbon that this is. So after we look at the type of carbon, we look at the nucleophile. Is it a strong nucleophile or is it a weak nucleophile? Now remember with Na plus is just a way to bring an anion into solution. So we see NaOH, right, NaNH2. It's just a way to bring an anion in. So really we're not focusing on this Na at all. We're focusing on this OH minus. So our focus is hydroxide. You don't see that it's negatively charged here because to bring an anion into solution, you have to bring it in as a salt. But what we don't, right, when we ignore that Na plus, now we can see that this is hydroxide. Is hydroxide a strong or a weak nucleophile? It's strong, right? It has that negative charge. So this is going to be a strong nucleophile. Now, the importance of a strong nucleophile, I'm going to probably write more on the first couple practice slides just so that we keep thinking about it. A strong nucleophile can attack, I'm just going to say at once. Meaning that it can attack in a single-step reaction. If it's strong, it can attack without a carbocation needing to form. So we know it's a strong nucleophile. Now we look at the type of solvent. So the solvent is typically underneath the arrow if you have a nucleophile above. So DMSO, if you have a solvent that has an abbreviation, it's probably going to be aprotic. So DMSO, THF, those are aprotic solvents. So I'm going to label this aprotic. So we have a secondary carbon, which could be SN1 or SN2, but then we have a strong nucleophile and an aprotic solvent. So if you flip back to that recap slide and you look at the type of reaction that can occur, is this more likely to be SN1 or SN2? 2, right? It's going to be SN2. Because a strong nucleophile can attack and kick the leaving group out. It has that strength to attack and kick that leaving group out all at once. I'll show you the mechanism. I'll go down and around. But some things we keep in mind for SN2 reactions. It's a single-step reaction. So it's a one-step mechanism. And in the notes, it talks about how the nucleophile will attack from the opposite side. So this is coming out towards you. It's going to attack from the back. And so since it attacks from the back, it's an inversion of stereochemistry. Right, inversion of stereochem. So what that means is this starts as a wedge. Our ending product should be a dash. So since this happens all at once, we still want to show the mechanism. So as we go through the mechanism, we're showing our curved arrows, being specific. Where's it going to? Where's it going from? So this happens all at once. So what happens, it doesn't matter which lone pair you bring it from, but you have that OH minus, that hydroxide anion, attacking that secondary alpha carbon, and as it attacks, it kicks the leaving group out. So this happens all at once. The OH minus attacks, the Br, that leaving group, is kicked out. So we look at our products. The Br was on a wedge. So now the OH is going to be on a dash. So it's an inversion of stereochemistry. If it was R, now it's S. So as you go through, right, and this is the mechanism. It's just a one-step mechanism for SN2. But with SN2, you have to have a strong nucleophile, and then an aprotic solvent helps to stabilize that strong nucleophile. Questions on this one before we look at the next? Okay, so the next one, and we're going to go through the same kind of thought process as we look at everything. So now when we look at our starting alkane, so all of these substitution reactions start with an alkane, all single bonds. I notice here now I just have one thing above the arrow. So I have CH3OH. Now I'm going to focus on my alpha carbon first. So here's my alpha carbon. All right, this one and this one would be beta, if you're looking at alpha versus beta. So there's our alpha carbon. Is this primary, secondary, or tertiary? Secondary, has two other carbons connected to it. So again, secondary could be SN1, could be SN2. A lot of what we look at is going to be secondary because we have to pick which reaction will occur. After we look at the type of carbon We're not limited to the reaction based on the carbon. Now we look at what's above the arrow. In this case, our nucleophile and our solvent are the same substance. So this is methanol. Would you classify methanol as a strong or a weak nucleophile? Weak, right? Water and alcohol are weak nucleophiles. So if you need to make yourself a note somewhere, right, on your notes, water and alcohol are weak nucleophiles. This is not negatively charged. And you say, yeah, but what if I take the H off? This is covalent. It's a covalent compound. You can't just pull the H off, right, and say that it's negatively charged. If this were an Na, right, then you could pull Na plus off and you'd have an anion. But this is a covalent compound. It's a molecule. So this is, oh, I guess N would be the S. Right? It's just a weak nucleophile. Now this is also the solvent. Can methanol hydrogen bond? Yes, it has H covalently bonded to NO or F. Right here. If it can hydrogen bond, then it's a protic solvent. Now, weak nucleophiles cannot attack in a single-step mechanism. Right, weak nucleophiles cannot attack in a single-step mechanism because it does not have the strength. So if there's a weak nucleophile, it's going to have to be a two-step process. It's going to be a two-step mechanism. Protic solvent favors that process. So which type of reaction is two steps? SN1 or SN2? SN1. So this is going to proceed via an SN1 mechanism. Now here's where we're going to have to look at a few different things as we go through the mechanism. So some things to think about with SN1. All right, this is two steps. So it's a two-step mechanism. One of the steps is carbocation being formed. So we have to pay attention to methyl and hydride shifts, all right, if they're possible. And then our products are 50% and 50% in terms of stereochemistry. Creates a racemic mixture. So 50% will keep the original stereochemistry, the other 50% will invert the stereochemistry. So we have two major products when it comes to SN1 reactions. So now we look at the mechanism that occurs. So I'm going to use the black marker just so that you can see how the arrows move, and I'll go down and around like we have with mechanisms before. So the first step in an SN1 reaction is the leaving group leaves. So the leaving group leaves, I'm going to draw the electrons from that bond going to the bromine. And when the leaving group leaves, we have there's our positive. Now this is secondary. Can I move to one side or the other to have a more stable carbocation? No, I move to either side, it's still secondary. So there's not going to be a hydride or methyl. We don't even have a methyl to shift. We won't have a hydride shift because you can only move one carbon over. So now we have this carbocation, that's step one. Then step two is our nucleophile comes in and attacks. So our nucleophile is CH3OH. So CH3OH, I'm going to show the lone pairs so you can see how this is attacking. So electrons from one of the lone pairs is going to attack the carbocation carbon, right, that positively charged carbon. When this lone pair attacks, it creates a single bond. We have to pay attention to formal charge still. This is very much like the acid catalyzed addition of an alcohol that we looked at with alkenes. So it's going to look like OH. I'm just going to do CH3. Now, there is still one lone pair here. Is oxygen right now in its most preferred bonding pattern? No, because oxygen, its preferred bonding pattern is 2 bonds and 2 lone pairs. So this oxygen right now has a positive formal charge, which means we're not quite done. So that second step is the weak nucleophile attacking, but we have to make sure that we get to a point where if our starting alkane doesn't have any formal charges, then our product shouldn't either. Remember, if your oxygen has a formal charge, you can continue to use that solvent to bring the formal charge back down to 0. And so to do that, this is actually one of the things that on the acid catalyzed addition I saw people missing the most, was actually this step. And it wasn't knowing that the solvent attacks, it was where does the solvent attack and how does it attack. So this oxygen, one of the lone pairs is going to attack the hydrogen. That's going to create a single bond between that oxygen and that hydrogen. And then these bonding electrons will go to oxygen. Now what that's done is that has given oxygen 2 bonds, 2 lone pairs. So now we have to pay attention to stereochemistry, because this could have attacked from either side. Right? This methanol could have attacked from the front or it could have attacked from the back, which means this single bond right here could have been a wedge or it could have been a dash. They are both correct. Creating that racemic mixture means that we're going to see both products form. So if it were keeping the stereochemistry, it would look like this. If it were inverting the stereochemistry, it would be this. Now, could you keep it like we had it with the O and then connect it to the CH3? Yeah, it's the same thing. But these are both your products. All right, one of them will invert the stereochemistry. One of them will keep the stereochemistry. So you have 50% of this product and 50% of this product. You have 2 major products in an SN1 reaction. Biggest thing is remembering to pay attention to things like this, right, with your formal charge. Questions on this before we look at the next one? Right, computer's here. I want you to see, just to start, go through kind of like we've been doing, and I want you to label the alpha carbon, label the nucleophile, and label the solvent. All right, so label the alpha carbon, the nucleophile, and the solvent, because that's going to help us determine what type of reaction is more likely to occur. Remember, now see you have this Na. This is an ionic salt. Na plus is used to bring an anion into solution. So this is actually OCH3 minus. I just put the negative with the oxygen because that's where the formal charge is. THF, like DMSO, those are your common aprotic solvents. THF we saw during the hydroboration reaction with alkenes and alkynes. So now we look at this. We have a secondary carbon, right? Secondary carbon, we're not limited to one type of reaction over another. So we could have either one, which means we look at the nucleophile and we look at the solvent. If we have OCH3 minus, is that strong or weak? Strong, right? Because of that negative charge. So this is a strong nucleophile. And then an aprotic solvent. Is one type of reaction favored over another with these conditions?
Yeah.
Which one? SN2. So this is going to be an SN2 reaction. Now SN2 reactions are nice because they're single step. All right, so we're just going to have one step for our mechanism. Other thing we have to keep in mind, SN2, when it happens all at once, there's not space to attack the same way. So right now this bromine is going into the board, which means the nucleophile is going to attack from the front side. So if we look at this mechanism, again, happens all at once. One of the lone pairs, I'll draw it like this. I'll draw it this way just to show it's attacking from the front side. It's attacking this alpha carbon at the same time, kicking the leaving group out. That all happens at once. So when that OCH3 minus attacks, it's going to attack from the other side. It was a dash, now it's going to be a wedge. So you invert the stereochemistry, right? Because it has to attack from the other side. BR is going into the page right now, which means OCH3 is going to attack from the front, because there's not space for it to attack in the exact same location. So that's an SN2 reaction. If we look at the next one, I want to go through the exact same way that we've been going through. So label your carbon, label your nucleophile and your solvent. So go through, label your carbon, so your alpha carbon, where's your leaving group, and then your nucleophile and your solvent. Yeah. So with this alpha carbon, how would we classify this substitution? Is it primary, secondary, tertiary? It's primary, right? There's one carbon connected. Now, we have to pay attention to this primary, but I do want to look at the nucleophile and the solvent. ETOH is ethanol. Is ethanol a strong or a weak nucleophile? It's a weak nucleophile. Water and alcohol are weak nucleophiles. It does not have a positive charge. Can ethanol hydrogen bond? Yeah, right, this OH allows it to hydrogen bond, so this is a protic solvent. Now, without looking at our reactant, just looking at our conditions, remember a weak nucleophile cannot attack all at once. So it must be a two-step reaction. If it's a two-step reaction, which type is that? SN1 or SN2?
SN1.
SN1. However, what?
Primary.
It's primary. All right, so it must be a two-step reaction, which is SN1. However, this calls for a carbocation to be formed. If you look at this, the leaving group would leave. I think that was enough. You would have a primary carbocation. Primary carbocations are not stable. They will not form. So, if this can't happen, this is going to be no reaction. So this is where you have to make sure that you pay attention to the type of carbon, the nucleophile, right? Protic solvent would favor SN1. We just can't have that. So oh wait, we have two more, okay. So for this one, see if you can work through this one with your groups. All right, I'll kind of go through it up here at the same time, so I'll just work through it up here, and then you can kind of check. I will tell you, it does not matter that this is a benzene ring. All right, so a benzene ring is just a six-sided ring with alternating double bonds. That doesn't matter with this reaction. You're focused on the single bond part with the leaving group. So still go through, label your carbon, label your nucleophile, your solvent, and see if you can work through and do the mechanism, show the stereochemistry, and then we'll kind of check answers. Okay, so hopefully, just based on what you have, you recognize that it's SN2, it's a single step, but still show the mechanism. So show the mechanism, keep in mind stereochemistry. So since it's SN2, you would see an inversion of stereochemistry. So you can see up on the board, it's a single step. I minus, being the strong nucleophile, will attack, but it's going to attack from the opposite side as Br leaves. So since Br was pointing, like facing towards you, that means that I minus has to attack from the back. So it's going to end up as dash. So questions on this one before we do our very last one for today. Okay, so the last one, again, I want you to start with your identification. Okay, so you go through, identify the alpha carbon, identify the nucleophile. We're doing this one last because we have to take a couple things into account. We're actually going to have two sets of products. Right, we're going to have a major set of products and a minor set of products. So when we look at this, we have I, and then it's a weak nucleophile, and it is a protic solvent, right? Water can hydrogen bond. Hopefully you remember from AP Chem that water can hydrogen bond, because that's what we talked about the most. And so since it's a weak nucleophile, this is how I like to remember it. Because it's weak, it has to have a carbocation form first. It cannot attack and kick the leaving group out all at the same time. So it's a weak nucleophile, which means it has to happen in multiple steps. If it happens in multiple steps, what type of reaction is it? Right, SN1. Can an SN1 reaction occur if it's a secondary carbon? Yeah. So now we're going to go through the SN1 mechanism. So happens in two steps. All right, first step is that the leaving group leaves. Our leaving group leaves, and we have, there's our carbocation. You have to be able to pay attention to the carbocation that is formed. Because what could happen to this carbocation? Right, so you could have a shift. Right? So you could have a shift here. Now, what I'm going to show is what happens if there's no shift. And then I'm also going to show what happens, right, if we have our shift. There's no methyl to move, so it has to be the hydrogen. All right, we have a methyl shift, hydride shift. This case is going to be the hydride shift. I will show that separately. I'm also going to show what happens if there is no shift, which is why we have two sets of products. We're going to have a set of minor products. We're going to have a set of major products. Every time I'm saying that we have this set of products, why do we have two minor products and two major products? It's 50-50, right? It's a racemic mixture. So what happens if there is no shift? Well, water is going to attack this carbocation. I didn't leave myself space for the rest of the mechanism. I'll show the rest of the mechanism for the hydride shift. Water is going to attack, right? That's going to put the OH up here. Here's our two minor. There's OH and there's OH. So there's our minor products. The OH is on that secondary. We could also have that hydride shift. So the hydrogen moves over one carbon. And we end up having a tertiary carbocation. And that's going to be the most stable. So now I'm going to show the whole mechanism. I skipped a step here because I didn't have the space. I'm going to show the whole thing here. I skipped the step where that hydrogen gets pulled off to create the OH. So we're going to have the lone pair attack. That's going to give us O single bonded to this carbon and also to two hydrogens with a lone pair. Here's the step that we didn't see going to the minor products. This will not work because there's still a formal charge. If oxygen does not have two bonds and two lone pairs, it's going to have a formal charge. So this is where we have more water because that's the solvent. Attack the hydrogen. Bonding electrons move. Our major products. Here's OH. Or here's OH. It's this step of the mechanism that people tend to leave out, and then they're like, where's the other hydrogen going? All right, so this is looking at the SN1. You have two major and two minor products due to that shift. Tomorrow we'll do the last page of the notes, which is practice.